Seismic data offers an opportunity to provide a detailed look at the geological structure beneath the Earth's surface. With the aid of a subsurface seismic image, prospective hydrocarbon accumulations are selected and drilled by exploration wells. The use of seismic technology is analogous to ultrasound technology, which is commonly used in the medical profession for imaging the human body. In the past, the distribution of discovered oil reserves has been uneven across the world. Historically, major oil-producing areas included the Middle East and the USA, both onshore and offshore. However, this is no longer the case, as the worldwide distribution of oil is more evenly distributed, as exploration activities have been successful in finding more reserves. For example, oil was first produced in the UK from the North Sea during the mid-1960s and continues to contribute significantly to the UK economy. As well as the historical areas continuing to produce oil, other areas, or more importantly other nations, participate in the global economy as a result of oil and natural gas production. Today, areas such as West Africa and Southeast Asia are among the list of major oil-producing regions. In recent years, offshore Brazil has witnessed a rapid expansion in exploration efforts. It is difficult to go through any part of any day in the 21st century without coming in contact with a product that is not derived from petroleum, from gasoline, heating oil, cosmetics and synthetic fabrics to plastics. Oil and natural gas are two of the Earth's most prolific natural resources, not only as an energy source, but also as a major commodity which is traded all over the world and is therefore an essential part of the global economy. It has remained an important Earth resource despite claims made in the 1970s that reserves would run dry by the year 2000 in areas such as the North Sea. This, however, is not the case. Although areas such as the North Sea are considered to be more mature oil-producing areas, modern seismic exploration methods provide a more detailed image of the subsurface than ever before, and the possibility of discovering oil and gas accumulations which had not been identified in the past. Such technology, coupled with improved exploration drilling capabilities, allows for more efficient production from existing reservoirs, which may have been close to exhaustion using older technology. In recent years, new reserves have been found as a result of seismic exploration efforts throughout the world's sedimentary basins. Once it has been concluded that a particular area is prospective for hydrocarbon reserves, seismic surveys are carried out in order to image the subsurface geology structure. Seismic data provides the first chance to look at the geological structure beneath the Earth's surface. With the aid of a subsurface seismic image, prospective hydrocarbon accumulations are selected and drilled by exploration wells, which will hopefully result in hydrocarbons being discovered. Production equipment is then put in place, and crude oil is transported either directly to a refinery by pipeline or indirectly by tanker. Marine geophysical operations are temporary undertakings, conducted by trained personnel utilizing carefully designed equipment and techniques.
Planet Earth. If you look closer, you'll see that a whole other world exists beneath the surface of land and sea. Layer after layer of rock structures go deep into the Earth's crust, mile after mile. And trapped within these structures, along with other liquids and solids, you'll often find deposits of oil and natural gas, the world's two most important sources of energy. These famous fuels are in constant demand because they make the world go round, day in and day out. So how do you find something that's completely hidden beneath the Earth's surface? It's a mystery that people in the oil and gas industry are always trying to solve, and for very good reason. Drilling for hydrocarbons is expensive. And before they spend money on equipment and crews, exploration and production companies need a reliable strategy for pinpointing where to drill. Geoscientists have a secret weapon called seismic exploration, and it involves sending acoustic energy, which takes the form of wavelets, into the ground to get a sound picture beneath the surface. It's complicated, so let's start with the analogy of bats. Bats can't see very well, so they send out little waves of sound that bounce off of objects and then go back to their ears. It's called sonar. It gives them what you might call a sound picture of their world. That's a good example of how nature already uses a form of seismic acoustic imaging to locate objects. Doctors also use it for ultrasound imaging. Geoscientists use man-made tools to make the sound wavelets, listen to them, and then record them. When you want to know if oil and gas deposits are in a particular area, geophysical companies bring large trucks that have big vibrators on them. Most of the time, this is what generates the acoustic energy or vibration. They use geophones, or very sensitive seismic microphones, to hear the reflected sounds, but sometimes they set off small buried charges. They set many geophones on the ground in a line, and they are attached to a recorder inside another truck. The vibrators send thousands of wavelets down into all the different layers of the earth. Some of the wavelets bounce off of the boundaries between the rocks below the surface and are reflected back to the geophones that are waiting to record them. Each geophone along the cable sends the received wavelets to the recording truck where they're recorded and stored. How do the wavelets reach into the subsurface of the ocean? That's offshore seismic, and it just requires a different device to send out the wavelets and record those that are reflected back. Out at sea, a seismic crew works off a vessel with a specially designed back end, so it's easier to lay floating cables or streamers. And all along the length of the streamers, microphones, called hydrophones, are attached one after another. Several of these hydrophone streamers are pulled behind the vessel at once. Acoustic sources are towed behind the vessel in front of the streamers and release compressed air, which creates the wavelets. These wavelets travel through the water and into the subsurface below, where, just like on land, they bounce off the rock layers and then return to the hydrophones to be recorded. Here's what seismic looks like after it's been recorded. Basically, it's a bunch of squiggles. There are still a few more steps to go before it begins to look like an actual picture of the Earth's interior. Right now, the data is still in its raw form. To get a picture that actually looks like the Earth beneath us, the data has to be processed. It takes a large supercomputing PC cluster to process the seismic data. These computers go through all the different traces made by the wavelets and filter out everything we don't need, such as vibrations made by a tractor in a field nearby. Using really amazing computer applications and working on state-of-the-art workstations, geoscientists can see the seismic data translated into a 3D picture. You might be thinking, I don't see any oil and gas there. But believe it or not, geoscientists can look at this processed data with their trained eyes and make an informed decision about whether or not oil and gas deposits are in the geologic structures. Seismic data leads to a high percentage of drilling success with less risk to the environment. And in a world where the demand for oil and gas is increasing faster than the supply, good seismic information will lead to more affordable energy.
In the beginning of June 2011, GeoNodal Solutions conducted the first tests of the equipment and exhibited the efficiency of the survey method. The survey was carried out in the Black Sea, not far from the Gelendzhik harbor. The unique technology of the seismic survey of offshore oil and gas fields benefits from the outstanding technological features and cost effectiveness. Due to the above-mentioned advantages, the technology itself and the first demonstration of the equipment and the surveying method captured the attention of 3 major Russian oil and gas companies. All 3 companies sent their representatives as observers for the pilot survey performed by GeoNodal Solutions. Alexei Khortov was representing the interest of Lukoil, Dmitry Vorobyov arrived from Rosneft, and Roman Piskunov acted as representative from Gazprom. The geonodes are being thoroughly checked and fine-tuned before being put into the sea. The equipment is fully ready for conducting a survey in the selected area. This time they will dive 30 meters. The geonodes can operate and collect high-quality seismic data in depths from 0 to 7,000 meters or 23,000 feet. The cutting-edge wireless control of the power supply and electronic components of the node and automatic time synchronization with GPS signals optimize the onboard setup node procedure. By means of all these innovations, the preparation time before the deployment of the nodes was cut to almost 0 compared to the competitive equipment developed by other companies. Moreover, the equipment produced by GeoNodal Solutions requires less staff to operate it. Once the vessel is in the work area, the node deployment begins. Each node dives to the seabed with an eco-friendly anchor, another innovation introduced by GeoNodal Solutions. Each node is deployed at the predetermined area of the sea surface and then dives to the desired spot on the seabed. Simultaneously, all deployments are recorded by the navigation software. This data will be used in the future to pick up the nodes upon release from the anchors. Upon receiving an acoustic signal from the vessel, the anchor will release the node and will remain on the seabed. It will disintegrate into silica sand and water, non-polluting components already contained in the seawater. In this way, the nodes are deployed in the survey area with equal intervals between them. Each node is fully self-contained and performs autonomic data recording. This unique technological advantage helps to achieve good coupling of the nodes with the seabed, making possible collection of top-quality data regardless of the bottom configuration. As a result of this, the rows of the nodes form plain, two-dimensional grid. Once the deployment of the nodes is completed, the second phase of the survey begins, shooting from the vessel with a seismic energy source. The air gun is being submerged into the water and then it shoots, producing seismic waves by discharging the pressurized air into the water. The source vessel shoots along the survey lines. Survey shooting lines are set up into the navigational software according to the survey plan. The final data processing of all performed shots recorded by all nodes makes it possible to form a deep image of the surveying area. The seismic energy propagates downwards to the Earth and then comes back, reflected from heterogeneous structures. When the reflected waves reach the seabed, they are being recorded by the geonodes located on the sea bottom. Due to the low power consumption of the geonodes, the operation survey time could be significantly increased. The geonodes can be deployed for different seabed positions numerous times without any need for replacing the power supply module. All these technological advantages result in increased productivity of the survey and decreased cost for the customer. The next phase of the survey is the picking up of the geonodes with recorded data from the seabed. In order to provide communication between the vessel and the geonodes, a special hydroacoustic transmitter is submerged in the water. Each geonode has a unique code number which can be easily found in the survey monitoring software. A special geonode deck box with acoustic transmitter is used to communicate with the geonodes and send commands for node release. The node vessel goes into the first line of the grid and transmits a pop-up signal to the geonodes in the line. Once the signal is received, the geonodes switch from the low power mode to the Eco Anchor release mode. Upon release from the eco-friendly anchors, the geonodes start to ascend to the sea surface. The nodes float up to the surface at the same places where they were deployed. After surfacing, they are collected from the sea surface with specially designed equipment or collected manually by the crew. Once on deck, the geonodes are carried to the wireless terminal for backing up of the recorded data. While the recorded data is being backed up to the terminal, a new eco-friendly anchor is being attached to the geonode. Upon completion of the above-mentioned procedures, the geonodes from the recently collected line of the grid are ready for deployment on the new line of the grid. The key to the operational efficiency of the surveying of the defined area is the transfer of data from the geonodes to the terminal. One of the major competitive advantages of GeoNodal Solutions equipment is the radio transparent case of the instruments and the high-speed data transfer between GeoNode and the terminal. The sea phase of the project is completed when all nodes are picked up from the seabed with the recorded data. Now the collected data is going to be processed and interpreted to provide the client with complete information about the geological structure. In August 2011, GeoNodal Solutions successfully completed a challenging project near Myanmar. There were a number of failed attempts to survey that area in the previous years by other major geophysical surveying companies. In January 2012, GeoNodal Solutions won a tender held by ONGC for the Deepwater Seabed Seismic Data Acquisition Project. The project data will be submitted to the client summer of 2012. GeoNodal Solutions was awarded Best Geological Exploration Technology of 2012 at the Russian Shelf 2012 International Exhibition.